let me introduce you to our wonderful staff of engineers. Today we have Eleanor Alley, our local skeleton model maker, Pavel Peshkovsky, our head warrior, Luke Molino, our devil's advocate, and Mark Dyndiuk, the lead procrastinator. Together, we have developed a system that allows you to get your rage out. Today, we are presenting Slap Skelly, a machine that you can slap with all your might and it'll tell you just how hard you slapped. As with any good engineering problem, this project required planning. Initially, we were going to recreate an arm brace that measured how fast a person stabs a pumpkin. This idea was eventually scrapped as we wanted the machine to be easily enjoyed by everyone. That's when we had the bright idea to try and recreate a Halloween spin on the traditional punching machine. From there, we had to create models, code, test, and then adjust as problems showed up. And boy did they. Our biggest problem was the encoder we were provided. Let's talk about that. The rotary encoder. A powerful little tool. Let's talk about its insides. It has two little discs inside it. One has copper contact plates equally spaced out, while the other has contact brushes. When these contact brushes meet the copper plates, a single pulse is emitted. Depending on whether the rotor is spinning clockwise or counterclockwise, based off this, it will send an A to B or a B to A signal to the Arduino. As we know the encoder has 20 plates in one disc, we can say that there are 20 pulses in one revolution. This is our PPR, or pulses per revolution. This becomes more relevant when we need to code our Arduino. Before we get into the nitty-gritty, let's talk about how our encoder failed. Throughout the creation of Slap Skelly, we had to do testing. Our main focus during this time was finalizing our code. While we expected some failures, such as our flex coupler, we did not expect our encoder to fail. However, it did. After cracking it open, we discovered that one of the copper plates had come loose and was preventing the discs from freely spinning. This was a rather annoying setback to the project as we needed an encoder to produce data. Thankfully, we were able to source a stereo encoder and proceed with final assembly.
Now, we have our sensor. Since we are using a rotary encoder, we need to have a way to convert the motion of the skeleton head after it was smacked into revolutions. The easiest way to do that would be to just have the skeleton head spin. We can connect the rotary encoder to the axis about which this skeleton head spins. First, we will focus on the object we are smacking. To make calculating the moment of inertia a bit easier, we chose to make the head a cube, specifically a Minecraft skeleton head. We are also going to 3D print the head to give us some freedom with design and aesthetic features, such as these shaft holes and facial features. We also need the head to be able to withstand a full-out smack, so we use some adaptive cubic infill on the head to reinforce the walls and important features while still keeping the head as light and as hollow as possible. Next, we will use a steel shaft to connect the rotary encoder to the spinning head. We chose steel mainly because we had some scrap rebar that could be machined down and fit the parameters needed. The head and the steel shaft equate to roughly a kilogram of mass, and the rotary encoder doesn't exactly give off strong and sturdy vibes in any way, shape, or form. So to avoid damaging the encoder from any misalignment or wobble in the shaft, which will be our minor horizontal loading, we 3D printed a flexible coupling to put between the shaft and the rotary encoder. We now have the minimal horizontal loads covered, but to remove any major horizontal loads and the vertical loads, in this case the weight of the system, we place the shaft through two bearings with a maximum distance between themselves to minimize wobble, and the shoulder of the shaft stays resting on the shoulder of the top bearing to reduce any weight on the rest of the system. The bearings will help remove friction from the system as the shaft spins. They were remnants of some spare skateboard wheels. They are held in place with a press fit into some custom aluminum pillow blocks. There isn't much point to the rotary encoder if it spins with the system, so to constrain the encoder, we 3D printed a brace that would attach the encoder to the frame. Finally, how are we holding all of these components together? Luckily, there was some scrap 80-20 aluminum extrusion from a previous project along with a bunch of hardware for it. The 80-20 will help create a sturdy and rigid base that can be clamped down to a table when the smacking commences. That's a wrap for the assembly. We can officially hold everything together in one piece and smack the skeleton to our heart's content.
Code, the bane of every mechanical engineer's existence. But don't worry, I'm going to walk you through it so you don't get overwhelmed. Let's start at the very top of the code, where we define our constants. They tell the Arduino exactly how to behave. We define the encoder pulses per rotation as 5,120. This tells the Arduino how many pulses the rotary encoder generates for one complete rotation. In our case, it's 5,120. Now let's look at the variables. These are where we store the data we're working with, like counting pulses, measuring speed, and calculating force. Here's encoder value equals 0. It's marked as volatile because its value can change at any moment, even outside the main loop, thanks to the interrupt function. Then, we have interval equals 5. This is how often we update our readings. In our case, every 5 milliseconds. Next, pin mode. This tells the Arduino to treat pin 13, the one we hooked up the encoder to, as an input with an internal pull-up resistor. This is necessary to make sure the pin is at a known state, in this case, high, when the encoder isn't actively sending a pulse. Then, attach interrupt. This is the magic. It tells the Arduino to pay attention to pin 13 and to call the update encoder function every time it detects a rising edge, meaning the signal goes from low to high. Every pulse from the encoder triggers this interrupt, which increases the encoder value by 1. Now, the real action happens inside the loop. This is where we calculate RPM, radians per second, and force every time the loop runs. First, we calculate the RPM. This formula takes the number of pulses from the encoder, multiplies it by 60,000 to convert from milliseconds to minutes, divides by the interval, and then divides by the total pulses per rotation. This turns the raw pulses from the encoder into the number of rotations per minute. Next is the force calculation. This beast uses physics to calculate the force exerted on an object using angular acceleration. This one's a little more complicated than the other calculations, but here's the breakdown. We're measuring how much the speed changed between the last loop and the current loop, multiplying it by the moment of inertia of the head and rod, which we calculated by assuming the skeleton head was a cube with uniformly distributed mass, and adding the inertia of the rod, approximated as a uniform cylinder. We then divided that by the measurement interval, and then divided the whole thing by half the side length of the skeleton head. Finally, we print out all the values, pulses, RPM, and force, so we can monitor everything in real time using the serial monitor and serial plotter. Lastly, the update encoder function. This is where every pulse on pin 13 increases the encoder count by 1. Simple but crucial. Every time the encoder sends a pulse, this function increments the encoder value. This is how we keep track of how far the encoder has rotated. And there you have it. We've broken down the Arduino code from start to finish, covering everything from defining variables to encoder pulse counting, as well as calculating velocity and force using a rotary encoder. Now that our code works, we can output the force of a slap in real time to the serial plotter. And as you can see, the force of a slap is about 300 newtons.
So, as with most projects, we learned a whole lot throughout the process of building the Slap-A-Skeleton. We completed several of the learning goals we had set for ourselves, like learning how to use a rotary encoder and how to code using an Arduino. We also learned some things the hard way, like the fact that encoders like the one we used aren't really meant to measure speed. These encoders with only like 20 pulses per revolution are really meant for low-speed incremental applications, like a volume knob in a car. For our application, we should have had an encoder with a lot more pulses per revolution so that we would be able to take more samples in a shorter amount of time. Also, for higher speed applications like ours, most engineers use optical encoders instead of mechanical ones like ours. These use small beams of light and light sensors instead of the copper connections that mechanical encoders use, which allows them to be significantly more accurate since they're not relying on mechanical connections that can wear out and fail, like ours did. Another thing we learned is that making sure that several things are aligned to a central shaft can be difficult. We also learned the hard way that designing for bearings is a bit more difficult than one might imagine. We wanted the bearings to be pressed into the pillow blocks, but we didn't use the correct type of press or leave space for the inner part of the bearings to spin, so they didn't spin as well as they should have. We also had trouble machining the rebar because it deflected a lot in the lathe, so it was a slip fit through the inner part of the bearings, which isn't really how that's supposed to work. If we were to make this assembly again, we would design the base differently in a way that would make it easier to align the shaft and keep it from wobbling. Overall, though, we're really happy with the way the Slap-A-Skeleton turned out. We had a great time building it, and we hope y'all enjoyed our video. Thanks for watching!